is live now, or it's available, so don't forget you have quiz 7 today. We're going to be doing this one. And we're going to be picking up with where we left off from Tuesday. So we're going to get as far as we can. We're not going to finish chapter 7 today. And then either this evening or tomorrow morning, I'm going to record and post, probably, just being totally honest with you guys, probably about 2 15-minute videos, one on equilibrium and one on, it's called Le Chatelier's principle. Those are the last 2 topics in chapter 7. And I just, being realistic, I need to teach at a slow pace, right? So I don't need to go too fast. And just with the pace that we need to go, I'm not going to get to those today. If I rushed really fast, maybe we could get there, but that would not do you guys any good. So I'll post those videos and then just watch those and take notes over spring break, or, by the end of this week. Because when you come back from spring break, the following week, we're going to be doing, well, I have the syllabus right here. The lab that we're going to be doing is Le Chatelier's principle. Yep. So you're going to come into lab. So you Monday people who have lab on Monday, I'm going to probably send an email reminder like the last day of spring break, this Sunday. So a week from Sunday. And you will be coming in, and the way it is set up, if you look at the lab schedule on the syllabus, we're going to break lab up half and half. So everybody will come in that Monday, but group A people, remember the lab sheet if you're group A, group B. Group A people will come in for the first hour, and then the group B people will come in for the second hour. All right, so everybody will come in same day, but we're going to split up half and half the lab time. We have a 2-hour window of time, so that's the way it will work. So just remember what group you're in. That sheet is in the labs folder on Blackboard. And please have watched the Le Chatelier's principle video, that concept, so that you're kind of at least familiar with what we're going to do when you come into lab. Okay, I think that's it. Be working on your chapter 7 homework, and I think most of you, unless you have lab tomorrow, should have the dry lab done. So any questions from you guys before we get started? All right, so we're going to go to the slide that has the deck of cards on it, if you have your lecture slides. And we were talking about enthalpy. There it goes. Right here. So Tuesday, we introduced the idea, the concept of enthalpy, and then we got to a little bit of entropy. And remember, these are 2 of the 3 puzzle pieces that help us answer the question of how do we know if a reaction is going to occur? And what's favorable for our bodies, what's favorable just in nature, how reactions happen or why they don't. And this is kind of where we left off. So just a little bit of review. We said entropy, the definition of it is a measure of disorder in a system. Okay, that's kind of a vague word at first, but then we're going to look at how we measure disorder and what increases disorder and what decreases disorder. We said the units for delta S are calories per mole Kelvin, and that's different from delta H, which is kcal per mole. So we'll come back to that in a little bit as well. We wrote those differences out, and then we said processes for which delta S is positive, where in a reaction disorder is increasing, those tend to be spontaneous or favorable. Okay. So then we looked at this figure, and I want to recap on this for just a second. If you're reading this figure from left to right, entropy is increasing. So if you have on the reactant side, if you have solids or liquids and you're making liquids or gases, the disorder in that reaction is increasing because physical states of things that are in a liquid state or in a gaseous state, those are more disordered because the molecules move around more and more and more and move with faster speed, more energy. Then if you have fewer moles, fewer reactants and you're making more products, like a decomposition reaction, entropy is increasing, okay, because you're going from fewer things to more things. And then vice versa, if you read the figure from right to left, that is where entropy is decreasing, okay? So if you have something that's a gas and it's condensing to a liquid or solid, or if you have more moles of stuff on your reactant side and you're making fewer moles, okay, so like a synthesis reaction, entropy decreases. Then we looked over here at this reaction and we added up the number of moles of stuff. It would happen to all be gases for the reactant of the products. And we said we've got 4 moles on the reactant side. We only have 2 moles of stuff of a product on the product side. So entropy is decreasing because you're going from more things to fewer things, which kind of matches this direction right here. More things to fewer things. Okay, so entropy is decreasing. The example your book gives too is like a deck of cards nicely stacked versus scattered about. Obviously, the nicely stacked deck, things are more ordered. The stuff scattered about, more disordered. Okay, so that's why they said positive delta S entropy increases on a simple process like that. Okay, question so far on entropy. We're going to do a poll question. I'm going to do the first one with you, and then I'm going to have you do the next 2 on your own. So I want to know for these 3 reactions, what is the sign on delta S? And then how do we know? How can we tell? So for the first one, we have, what is this compound right here? NaHCO3. Can anybody name that? HCO3 is a polyatomic. It's important physiologically too. Thank you, Molly. Sodium bicarbonate. So it's a solid. All right. And what's happening is I have two moles of sodium bicarbonate breaking down into sodium carbonate, water, and CO2. Sodium carbonate's a solid, water's a liquid, CO2 is a gas. So we have something that's just a solid on the reactant side, and we only have 1 reactant. So this is like decomposition if we had to classify it. And I've got 1 mole of a solid, 1 mole of a liquid, 1 mole of a gas. I think it should be balanced. So do you think delta S is increasing, disorder is increasing or decreasing? So is delta S positive or negative here? Kristen says increasing, and I agree. It's a positive delta S. Okay, this side is more disordered. So delta S is increasing. All right, so with the same kind of logic, let me launch the poll. You guys do the second and the third one on your own. And then put your answers in here. And I think they should already be balanced for you, so you don't have to worry about that. Also, in case you guys have wondered how my morning's gone, you know it's a good morning when your son poops out of his diaper everywhere. You gotta change his diaper and you're like, dude, why were you even wearing a diaper? Because you didn't, like, I don't understand how this happened. So that's been my morning. It was good, really good. Sometimes I'm like, how do babies do that? Like, this got all the way up to your neck. Like, how does this happen? Anybody been there before? Changed one of those? All right, give you just a few more. We're 83% voted, so if you haven't got your answers in, we're gonna go over these. Give you just a little more time. All right, I don't see the numbers going up anymore. Number 1, we got some mixed reviews. Number 2, most people picked negative, but for number 1, well, it says equation 2. Okay, so for equation 2, most people said delta S is positive, but a lot of people also said it's negative, so let's see. Here's what I notice about number 2, just right off the bat. We've got gas and gas on the reactant side, and then we've got a gas and a liquid. Okay, so for this, we've got 3, how many times do I do that? 3 moles of things that are all gas. And then over here, we have 1 mole of something that is a gas. And then we have 2 moles of something that is a liquid. Okay. Now, remember from the figure right up here, liquids compared to gases. Are liquids more disordered than gases? What do you think? Which one's more disordered? Gases are more disordered, right? The molecules are just a little more crazy, okay? Gases, they're a little closer together. They have less energy, so they're more ordered. Okay, so if we have more moles of liquid on the product side, we have more order. Over here, we have more disorder over here. We have 3 moles of stuff on each side, so we can't necessarily judge it this way, more moles to fewer moles. But we can look at the physical state here and say everything's a gas on the reactant side, but not everything's a gas on the product side. More things are liquid on the product side. So that's how I would have judged this one. So you're becoming more ordered, which means disorder is decreasing. Okay, so it should have been a negative delta S. Again, you're not judging order, you're judging disorder. Okay, so that one is a little confusing, but it's a negative delta S. All right, so disorder is decreasing there. All right, and then if you were half awake this morning, we actually looked at this one on the slide above. Into an H3 makes an H3. So we have 4 moles of everything is a gas on the reactant side, and we only have 2 moles. Everything is still a gas on the product side. So somebody double check, make sure you're muted. I think we got it. So we have more moles to fewer moles. Here, the physical state, that should be MOLS. The physical state is not what matters here. So we're really not judging based on anything up here. We're looking at the number of moles. So here it is going from 4 to 2, so decreasing. So it should be a negative delta S as well, which is what most people pick for number 3. Okay, so questions on how to judge this. You're going to have to do this on exam 3. Look at a reaction and tell me if delta S is negative or positive. Okay, so with that, that's it for entropy, by the way. So we got enthalpy and entropy. Now we're going to move to Gibbs free energies, the third puzzle piece. And really all we're going to do here is we're going to take puzzle pieces 1 and 2 and we're going to put them all together. Okay, so what we've learned so far is that if you have a negative, I'm not going to write the full words, I'm just going to write the signs, the mathematic signs. Oops. If you have a negative delta H, we said that is favorable, right? And another word for favorable, I'm just going to abbreviate, is spontaneous. Okay, so that reaction will be spontaneous. And we said processes for which delta S is positive tend to be favorable. So we need a positive in that column. So when you have this combo between your delta H and your delta S, you're going to get a reaction that's spontaneous and that is favorable. And you can write always, if you want, right there. Always favorable, always spontaneous. When you have this combo together, a reaction that has both a negative delta H and a positive delta S. On the flip side, if you have a positive delta H and a negative delta S, disorder is decreasing, you get one that is unfavorable. Okay, and you can write always. So it's non-spontaneous. Now, what if we have I mean, there's more combinations, right? What if we have negative, negative? And what if we have positive, positive? Then we don't know. It's a little more complicated. This is where the third puzzle piece comes in. So we have an equation for Gibbs free energy. And this equation is going to help us figure out scenarios 3 and 4 on the table. Okay, what happens when you have both a negative delta H, negative delta S? So the equation is this. Gibbs free energy, by the way, we abbreviate delta G. That's Gibbs free energy. And the equation for this is the combination of a delta H and a delta S. And it looks like this. Delta G equals your change in enthalpy, delta H, minus whatever your temperature is, T for temperature, and we're going to multiply the temperature times delta S. Okay, so delta G equals, this is your change in enthalpy, minus the temperature times the entropy term, change in entropy. Delta G equals delta H minus T delta S. Okay, so I want to review a little mathematical principle here. It's a very simple one, but it has to do with negatives and positives. Okay, remember this. I'm going to zoom into some white space here. If you have a positive, and then we have this minus sign right up here. So if you had a positive delta H and then a minus, and then temperature, by the way, will always be positive. Okay, this will always be a positive number. You're not going to have negative temperatures because we're going to be in the Kelvin scale. So you can never have a negative Kelvin. The lowest it can go is 0. All right, so always have a positive temperature. So always have a positive there. But your delta S can be positive or negative. So if we have a positive delta S, I'm just looking at these two, and these are multiplied, right? The temperature and the delta S are multiplied. So positive number times a positive number is a positive number, right? But when you put this negative out front, it makes this whole thing negative, right? Okay, so remember order of operations type of stuff. Well, what if my delta S is negative? A positive and a negative, that makes a negative number overall, right? And a minus a negative number is what?
Plus.
A positive, right? So if we do subtraction on a negative number, that becomes positive. So a minus negative actually makes this whole thing positive, okay? So just remember that. That's math there as you go about some of this, okay? Okay. So the table we filled out is kind of also right down here. And we have an added column for delta G on this table now. Because when you start to work the math out and you've got the negatives and the positives, we said this is always spontaneous. Why? Because it's always mathematically going to give you a negative delta G, okay? So now, instead of looking at a delta H and a delta S, we can just look at the sign of delta G, one sign, and determine if something's going to be spontaneous or favorable or non-spontaneous or unfavorable, okay? So I want to tell you, delta H and delta S are kind of indirect ways to determine if a reaction is going to happen or not. Delta G is the direct way to look at it and just say, oh, it's negative, boom, it means this, spontaneous. If it's positive, that means it's always non-spontaneous, okay? And remember, the combinations of these delta H's and delta S will give you these delta G's, all right? Now, again, if we have a positive and a positive or a negative and a negative delta H and delta S, then we have to use the equation and actually calculate our delta G and just see if it's positive or negative, okay? So a little bit more about delta G. If we have a negative delta G, we call this reaction exergonic. Kind of like exothermic, right? But not the same word. It's a little bit different. So make sure you keep exothermic and exergonic separated. Exergonic means a negative delta G. Exothermic means a negative delta H. Okay, so if we have a exergonic negative delta G, you guys tell me, is the reaction spontaneous or non-spontaneous? From looking at the table.
Spontaneous.
That's correct. So is energy released or absorbed? There, look at your delta H. You guys remember that's what tells us about whether energy is released or absorbed. Exothermic energy is released, endothermic energy is absorbed. Heat. So when you have a negative delta G, we see a negative delta H here, energy is always going to be released. okay? And therefore the products are lower in energy, which means more stable than the reactants. Okay, remember that little energy diagram we drew? Okay, on the flip side, we have a positive delta G. The reaction is called endergonic. I think they want you guys to get them confused, so they just made the words very similar, right? Just kidding. The reaction is endergonic when you have a positive delta G, and therefore it is non-spontaneous. The reaction will not happen on its own if you have a positive delta G. Energy is absorbed in these reactions, and the products are higher in energy, which means less stable, okay, than the reactants. So that's a little bit just vocabulary stuff about delta G. Questions so far? We're actually going to put all this together. We're going to use the math equation now. So you guys remember how we talked about ice melting the other day? We're actually going to work a problem on that now. So we talked about if you take ice out of the freezer and you put it on a plate and it starts to melt in the liquid water, we know that process is just spontaneous. We don't have to do anything. It just happens. And that's kind of the chemical reaction for it. If we are actually given a numerical value for delta H, 1.44 kcal per mole, it's a positive delta H because we said the process is endothermic because it's absorbing heat. Ice has to absorb heat to melt. That makes sense. And then liquid is more inherently disordered than a solid. So the delta S makes sense that it's positive here. Disorder is increasing. So we have this value too. So now we're going to calculate what is delta G if we have 3 different temperatures, okay? And I may not actually take the time to work out all 3 so that we can move on. But once I work it for one temperature, you work it the exact same way for the other temperatures, okay? The first thing we do, there are 2 steps, 2 kind of like preliminary steps you need to make sure of before you just plug everything into the equation. Step number 1, your temperature must be in Kelvin. And notice conveniently it's not. Okay, so we're gonna have to put our temperatures in Kelvin. That's not hard though. Remember, how do you convert Celsius to Kelvin? You add what? What's the number? Thank you, Molly. 273.15. Step number 2 is that you must make sure units for delta S and delta H match. So what I like to do is I just convert calories to kcals, all right? And so I just take my delta S and I convert calories. I'll actually write that right up here. I convert the calories to kcals because we can't add and subtract things that are, I can't add and subtract calories with kcals. They have to either both be in kcals or both be in calories, all right? Okay, so step number 1, well, let's just work it with the negative 10 degrees Celsius. You can have a negative Celsius, but you cannot have a negative Kelvin temperature, all right? So let's take negative 10, we're gonna add, and this is degrees Celsius, the 273.15 Kelvin, so this is step number 1, and we get 263.15 Kelvin, right? So we took care of the temperature thing, and now we need to convert our delta S to kcal. So what is our delta S? It is 5.25 calories per mole Kelvin. Oh, sorry, 5.26 calories per mole Kelvin, 5.26. So I'm gonna come down here. We got delta S, 5.26 calories, and please write it like this, per mole Kelvin. So how do we convert calories to kcals? We want calories to cancel. We want to end up with kilocalories. So we need the relationship for this, right? How many calories equals 1 kcal? You guys remember? How many calories are in a kcal?
Thousand.
Yeah, thank you. 1,000. So I'm going to write 1,000 calories on the bottom down here for every 1 kcal. So we're just going to divide this number by 1,000. So really, just move the decimal 3 places to the left, okay? Or you can plug it in your calculator, no big deal. but you should get 0.00526. Now you have kcal per mole Kelvin. Don't forget calories cancel and you have calories per mole Kelvin. Boom, boom. All right, so that's part 1 is done and part 2. Now we can plug everything in. So what's our equation? Delta G. Remember, it's delta G equals delta H minus T delta S. So we're just going to plug everything in and solve for delta G. So our delta H, we got to go get that. That's the first thing we plug in. Delta H is 1.44 kcal per mole. So we got 1.44 kcal per mole. There's our delta H. We're going to do minus, what's our temperature? We determined that right here in Kelvin. I'm going to put all this in parentheses, by the way. I like to put my T, my temperature, my delta S in parentheses. So 263.15 Kelvin. Then we do times. These are multiplied by each other. Here's our new delta S. So the 0.00526 kcal per mole. There's a lot of units. I know, this is messy. And what you should see happen, you got Kelvin on the top with your temperature term, Kelvin on the bottom with your delta S term, those cancel. And look what beautifully happens, kcal per mole with the delta S and kcal per mole for the delta H. Now we can add and subtract. So first, do the T times the delta S part, 263.15 times the 0.00526, get that term. Then you do the 1.44 minus that. And what do you guys get for delta G? So you should be doing in your calculator 263.15 times 0.00526. You get that number, then you do 1.44 minus that because your units now match and you can just subtract those. Anybody get the answer for us? Okay, Rachel and Kristen both seem to get 0.05 and if you round 5.6. 0.056, and what are the units on that? Kcal per mole. So that is our delta G. And what do you notice? That delta G is positive. So is this reaction going to happen or no? Is ice going to melt at negative 10 degrees Celsius or will it stay a solid? If it's a positive delta G, the reaction is, we call it endergonic, which means it's non-spontaneous. Okay, so it will not happen. It's a non-spontaneous reaction, not favorable. So ice won't melt at negative 10 degrees, in case you were wondering. All right, so then for 0 degrees Celsius and 10 degrees Celsius, you would literally do the same exact steps. Convert your temperature to Kelvin. You've already got the delta S, it's right here. You don't have to recalculate that every single time. So you just plug the new temperature in to the same equation down here. This number, the 1.44, and those numbers don't change. And you just recalculate it and see what your new delta G is. I bet as you increase temperature, you eventually get a negative delta G. It's pretty close to 0, and so I bet eventually it swings positive when you raise the temperature high enough. Okay, so this brings up an interesting point. When you have a scenario where you have a positive delta H and a positive delta S, let's go back to the table. That is which column here? That's right here. When you have a positive and a positive, as you increase temperature at higher and higher temperatures, your delta G eventually becomes negative. I'm going to say that again. As you increase temperature, your delta G eventually becomes negative. We got some in the chat. I'm not going to lie. This is really confusing. My brain is fried from all these times. Yes, I agree with everything Gabrielle just said. This stuff is confusing. There's so many different layers here and signs and pieces to the puzzle. Okay. So I don't expect this to all sink in day one. This is going to take some practice. We're going to do a few more practice problems on this. I'm not just going to move on to the next thing. But I did want to bring this point up. I'm going to draw a little arrow to column 3 right here. Delta G can become negative at higher temperatures. Okay, so when you have the positive scenario, you're more likely to get a spontaneous reaction at higher temperatures. Non-spontaneous reaction, so it's very temperature dependent. Scenarios 3 and 4. So guess what? Scenario 4, delta G can become negative. It's the opposite at lower temps. All right, so just make note of that. I know we haven't worked a problem that proves this just yet, but you will. And anyways, make note of those things. Okay, let's work another delta G problem. We're going to do another practice, maybe 1 or 2 more, and we'll see how we're doing on time. Okay, here's one right here. You have in the reaction carbon. It's a just solid carbon plus water, and we're making carbon monoxide gas and hydrogen gas. Okay, so look at, you've got the states of matter included for everything there. You've got solid and liquid on the reactant side, then you've got everything as a gas on the product side. I think it is balanced. It is. So here's the first question. Is entropy, remember this is the S term, increasing or decreasing?
Increasing?
Person says increasing. Anybody agree, disagree? If you agree with Christian, give me a thumbs up. If you disagree, give me thumbs down. Okay, I don't see any thumbs. All right. Okay, so yes, entropy is increasing. All right, we're becoming more, this side is more disordered. So it's increasing. So what that means, we have a positive delta S. Remember this is tending to be favorable. A positive delta S favors a negative delta G. Okay, and if delta H is negative 31.3 kcal per mole, and delta S, the actual value of it, if they give us a real value of 32 calories per mole Kelvin, is the reaction spontaneous at 27 degrees Celsius? Hold on, let me read in the chat. Riley says, so as the temperature goes up, delta G will be more negative, and if the temperature goes down, delta G will be more positive, right? Riley, that applies only for scenario 3 on the table. Okay, scenarios 1 and 2, where you have the negative, like for scenario 1, where you got negative delta H and positive delta S, that's always a negative delta G. You don't have to mess with the temperature or wonder, is it going to be if I increase temperature? No, it's just always a negative delta G. And then same for column 2. You got positive, but if you've got columns 3 and 4 where the signs on delta H and delta S match, either they're both positive or both negative, that's the 2 scenarios that are temperature dependent. And at higher temperatures, when both delta H and delta S are positive, you can tend to get a negative delta G. But at lower temperatures, when you've got negative and negative, then at lower temperatures, your delta G will tend to become negative. I hope that answered your question. If not, follow up with me on that. Okay, going back to this. So we've got real values for delta H now. Is the reaction spontaneous at 27 degrees Celsius? Well, first off, before we calculate it, why don't we just look at the signs? I notice we've got negative delta H and we've got positive delta S. So what do you guys think?
Favorable.
Yep, spontaneous always, doesn't matter. You could be 101 degrees Celsius. It could be negative 10 degrees Celsius. That reaction is always spontaneous. So yes, it will be spontaneous at any temperature. Now, question 3 says, what is delta G? So now we got to calculate it. Okay, so we're gonna do our steps here. We've got a temperature in Celsius. So the first one we got to do is convert it to Kelvin. So 27 degrees Celsius plus 273.15. That's step number 1. Always convert your temperature to Kelvin. So we get, what is it, 3.15? Is that right? I think so. And then step number 2 is let's take our delta S and convert the units from calories to kcals. So we've got 32 calories per mole Kelvin. I'm going to convert it to kcals. So we're just going to divide by 1,000. Calories cancel. So you do 32 divided by 1,000. So you're just taking the decimal place, moving it 3 places to the left. You should get 0.032. Now it's kcal per mole Kelvin. Okay, so now we got, this is T, this is temperature, this is our new delta S with kcals. Now we just plug everything in to delta G equation. I wish I could shrink it all down. I'm just gonna erase a little bit up here. Pull that back up. Okay, so delta G is gonna equal, let's plug in our delta H, which is right here, negative 31.3 kcal per mole. And then remember the equation is right here, delta H minus T delta S. So we got minus, and then I like to put this in brackets or parentheses. Our temperature, 300.15 Kelvin times 0.032 kcal per mole Kelvin. Okay, so first, Kristen said you got negative 40.9. Anybody else get that? You did 300.15 times 0.032, and then you did negative 31.3 minus that. All right, Kylie, Brooklyn also got the same thing. So our delta G here is a negative 40.9 kcal per mole. All right. And I think we got another one. Let's do one more. So on this reaction, we've got calcium carbonate. Is everybody hanging? Do I need to go back to the previous slide? Everybody got everything written down? You guys with us? Okay, I'm seeing head nods. That's good. Please turn your videos on, please. Can you, what is it, Whitney? You want me to go back up for a second? Okay. So we're gonna work one more problem, and then we need to get to reaction rates. All right. Is that good, Whitney? You still writing? Okay. So we got calcium carbonate in this reaction. It makes calcium oxide, which is a gas, and CO2, which is a gas. So we got something that's a solid, and then we got on the product side 2 things that are a gas. And we're given the delta G. So we see that the delta G is positive. That's the first thing you should always look for. What's my delta G, positive or negative? So this means non-spontaneous at this temperature. If temperature changes, sometimes, depending on what your delta H and delta S are, maybe that delta G could change. We'll see. So is this reaction spontaneous at 25? Well, we kind of answered that. We said it's non-spontaneous, so no. At that temperature, it is not spontaneous. But now let's look at scenario 2 here. Does entropy increase or decrease? What is the sign on your delta S?
It's increasing.
Yes, definitely increasing here. Solids, remember we said that when you look at physical states of matter, solids are very ordered, gases are very disordered. And so we're going from a solid, something very ordered, we're making gases that are disordered. So delta S is increasing for sure. We got a positive delta S here. Okay, so do you expect the reaction to be spontaneous at higher temperatures? This is an interesting question. Well, how do we know? So here's what I see. If we have the table, or we have our equation, delta G equals delta H minus T delta S. Here's what I know. Temperature, we said always has to be a positive number. And we see that our delta S is a positive number. Okay, so the fact that we have this big old minus sign out front makes this whole unit negative, right? And we have a positive delta G as well. Okay. Now, delta H. To get a positive delta G, remember there were two, I want to go back up to this table for a minute. This one right here. Let me erase a little bit because I've kind of scribbled all over it. So the question is, do we expect the reaction to become spontaneous at higher temperatures? Meaning, would we get a negative delta G if we keep raising the temperature? Okay. So we have what we have is a scenario that matches this right here. You aren't given delta H, but the only way you can have a positive delta G in this case is if your delta H is also positive. Okay. So I'm going to scroll right back down here. It must mean that we have to have a positive delta H here. So remember, this term, this minus sign, makes this whole term right here actually negative because we got two positive numbers in those brackets. So we've got scenario 3. This is scenario 3 from the table. And remember what we said about scenario 3? What did we say about it? We drew this arrow and said it can become negative at high enough temperatures. Okay. Sorry, I keep scrolling up and down, but do you expect the reaction to be spontaneous? Meaning, could we get a negative delta G at higher temperatures? And the answer here is yes. Let's do a little experiment with some very simple whole numbers. Let's say our delta H is 10, just plain old positive 10. And we say minus, let's say our temperature is a 1, just 1 Kelvin or whatever. And then let's say our delta S is 5, positive 5, because we know both of these numbers are positive. Okay, what is our delta G going to be if we have simple numbers like this? 10 minus 1 times 5, we're going to get positive 5, right? So at this temperature, a pretty low temperature, we get a positive delta G. But now let's say we bump the temperature up. Let's say we bump the temperature up, we multiply it times 10, crank it up to 10. Now we have same numbers for our delta H, but our temperature is the only thing that's different. If we increase the temperature to 10, so this one is at a higher temp. And we still got the same delta S. Now what is our delta G? You got 10 minus 10 times 5, so you should get negative 40, right? Okay, so you see how that works? At higher temperatures, when you have a positive and a positive, you can get a negative delta G. So if you ever want to run a little simple experiment like this yourself with just these simple whole numbers to double check, you can do the same and play with the temperature. Okay, I think I meant to do that on this next slide. I think that's why I put a blank slide in here, but I had plenty of space on this one. So I'm going to scroll past this one. All right, this is the last practice problem we're going to do on delta G, and then we're going to move on. I've got a very generalized equation here. A makes B and C. Whatever compound A is, it's a solid, and it breaks down into B and C. If you're a visual person, this one gave you a nice picture. Okay, it gives you the key. I don't know what just happened. It gives you the key right here. So these green spheres over here, this is A. It's a solid. You can see those spheres are ordered. They're nice and ordered. Yes, Gabby, I will go back up. Thank you for letting me know. And then on the product side, these little faded spheres, this is B. And all these gold spheres, this is C. And it's a gas because they're moving around filling the container. And that's what gas particles do. And it gives you the delta H, negative 23.5 kcal per mole. So from looking at the reaction, what's the sign on delta S? Are you becoming more ordered or more disordered?
Disordered.
Okay, so if we're becoming more disordered, does that mean your delta S is positive or negative? Okay, Kylie says negative. So this is more disorder. So remember, so Rachel says positive, Nada says positive. Kylie, remember we're not measuring order here, we're measuring disorder. Okay, that's where it gets confusing. Disorder is increasing, all right? So it's got to be a positive delta S. Disorder is increasing, so positive delta S. If order is increasing, it's a negative delta S. But here, disorder is increasing because gases are more disordered than solids when you're making a gas. You have only things that are solids on the reactant side. And look, you're going from one thing to two things. So inherently, it's a little more disordered as well. Okay, is the reaction spontaneous at all temperatures, some temperatures, or no temperatures? So the easiest way to answer these questions is to look at the sign. Can we figure out the sign on delta G? If my delta G is negative, then that is going to be spontaneous at all temps. If it's positive, then it's going to be non-spontaneous at all temps. Okay.
Delta G is negative.
Chris's delta G is negative. So Gabby also in the chat said, how do you know if they're negative or positive based on solid liquid gases? So Gabby, we're given delta H. We see it's negative. We already looked at delta S. We said delta S was positive. So based on that, go back to your table. Say, do I have row 1, 2, 3, or 4 off my table? If you go back and look at the table, when you have a negative delta H and a positive delta S, that corresponds to situation or row 1 on that table that we filled in. And on row 1, we said this always equals a negative delta G mathematically. You'll never get a positive number for your answer. It'll always be negative. So that means it is going to be spontaneous at all temperatures. Does that make sense, Gabby? Okay. Somebody asked me to scroll back up. Anybody still writing on this slide? I'm going to scroll back up to the previous slide for the person who needed it. And then that's it. We're going to move on to reaction rates. So that is delta G. On exam 3, you'll have a delta G question. It may be a concept question where I say, look at this, here's a delta H and a delta S. What do you think? Would delta G eventually become negative if you messed with the temperature? I might ask you to calculate your delta G. That could be a file response question where I want you to make sure you convert your temperature and change your delta S and plug it all in and solve for your delta G. We got some questions in the chat. Abby said, can you repeat what you said about knowing if they are positive or negative? You're talking about the delta G, right, Abby? Not a delta H or delta S? Okay, so if it all goes back to that table, and whoever needed this slide right here, are you good now? Can I scroll up to the table? Okay. It goes back to this right here, Abby. It just the signs. If you have, we saw in this in that problem, that very last one, I'm going to go back to that too, Kylie, that we had a negative delta H and a positive delta S. So therefore, delta G will always be negative, okay, when that's your situation, and at any temperature, all right? And then if delta H is positive, delta S is negative, vice versa, delta G will always be positive, okay? So you can always you should have this, you can use this table in the exam and just look at what you have and then make your judgments based on that. And then Kylie said, so in the chat, so the one before had 2 gases in the products and it was positive delta S. So why the one we did also I'm just sort of confused. Okay, hold on. Let's see what we're talking about here. All right, Kylie, what we had a solid and then we had 2 gases on the product side. And then on the one down here, we had a solid and a gas on the product side. So the fact that you have 2 gases on the product side versus 1 gas on the product side, that's not necessarily what matters. What matters is that you have solids on the reactant side and your product side is more disordered. On the reactant side, you just have one item. You just have one reactant. On the product side, you have 2 things. Now, the fact that one is a solid, yeah, if we just had solid to solid, sure, we'd have to look at how many moles and stuff like that. But the fact that we are making a product that is a gas, which gases are inherently more disordered because of their physical state, we know delta S is positive. And then it was the same thing for up here. We said delta S is positive as well, so it's positive for both. Okay. All right, now here's the deal. I tried to tell you guys chapter 7, it's hard, it's nuanced, there's a lot of little things. And it's not that any one of these individual steps are like insanely challenging. What's challenging about these problems is all of it put together, okay? They're hard, okay? So don't expect to just walk into the exam 3 and ace a problem like this without spending some time on it, without practicing. So I will definitely, like I do for every exam, I'll give you a list of recommended practice problems, practice these delta G things, and reach out to me if you have questions. I'm gonna review this before the exam. This is not the only time you're gonna see it. But these problems are challenging, some of the hardest that we're going to do. So, all right, that's the delta H, delta S, delta G stuff. That's all 3 pieces of the puzzle. Now we're going to talk about reaction rates. So we're switching to a new topic here in chapter 7. It's tied in with the stuff we've been talking about, but rate indicates speed, right? How fast or slow are things going to happen? When we're talking about the human body, obviously, if you eat a meal, I don't know about you, but depending on what meal it is, you get hungry again, okay? You don't stay full forever. Your body is digesting it. It's constantly immediately going to work, and all these reactions to break down the food and to extract the energy are happening in a very timely manner. And we need those things to happen very timely. We know there's other reactions just in nature that happen very slow, okay? Like landfills, the decomposition of waste is a very, very slow thing. And there's things you can do to help increase it or make it faster, but some reactions are just naturally slow, and then some reactions are naturally fast. So how do we determine if reactions are going to be fast or slow? If we need a reaction to be fast, how can we make it faster? We're going to look at some questions like this. So delta G only tells us if a reaction is going to happen or not. It doesn't tell us anything about how fast. If delta G is negative, the reaction will occur eventually, okay? We don't know when. Now, the rate or the speed of a reaction is determined by something we call efficient. Oops, I didn't spell that right. No, I did. Efficient collisions is right here, which just means the colliding of 2 or more molecules with correct orientation and sufficient energy to produce a reaction, okay? So molecules, they have to be facing the right way, they gotta be in correct position, and then they've gotta hit with some forcefulness, okay, for them to react. If they're not facing the right way and they don't have enough energy, they can collide all they want and you're not gonna get a reaction. A real example from your textbook it has to do with the ozone layer, okay? We've all heard of the ozone layer. So ozone looks like this. It's 3 oxygen atoms combined into 1 molecule. And also in the atmosphere, we have all kinds of nitrogen molecules. Nitrogen is like 78% of our atmosphere. So we've got a nitrogen and an oxygen atom here. If these 2 molecules collide and the nitrogen is facing this terminal oxygen right here, so these 2 are facing each other, when they collide right here, now they're attached, then you're going to get a reaction. Pernil in the chat said, is efficient collision the same as activation energy? It has a lot to do. We're actually headed towards activation energy, okay? There's Pernil, almost yes. It has a lot to do with it. So going back to this figure though, if these two molecules collide and it's the oxygens facing each other and the nitrogens on the other side, then you're not going to get a reaction because it's just not oriented the right way. Okay, so that's very detailed and very nuanced, but that's an example when we say it's got to have the right orientation. So I'm going to draw what we call a reaction diagram. It's going to look a little bit similar to what I drew on Tuesday. A reaction diagram, that's a very non-straight line. So draw this with me. Riley says, can you scroll up again? Yes, absolutely. Let me know when you're good, Riley. We're going to draw a reaction diagram and we're going to label several things. We labeled again, Tuesday I drew a very simple one with reactants and products and their energy levels. All right, I'm going to assume I can scroll down. Okay, so if we have, energy, and this time we're talking about the overall delta G energy, not just, it is a measure of potential energy. On the y-axis, and then we have reaction progress on the x-axis, okay? So you may have to draw one of these for the exam or label one of these on the exam, so please be ready to do that. So we know when we start any reaction, we have reactants, right? So let's just say arbitrarily, any reaction diagram is always going to have an energy level for your reactants. And I like to put an R for reactants here, okay? And then when we finish the reaction, we've got our products finally. And you know what? I'm just going to say this is going to be a favorable reaction. And our products are going to be more stable and lower in energy. So I'm going to draw my products right there at that level. Now, in between these two things is what I have not drawn yet, okay? And there's more to the story than what I drew on Tuesday. So any reaction is going to have some sort of peak, okay? Some sort of peak energy level that it must hit before the reaction will go. And this is what Pernille was saying in the chat earlier. This is the activation energy. So from the level of reactants, this energy level right here, all the way up to the top, okay? That difference between the peak and just your reactants, that is what we call activation energy. And we call that EACT, the activation energy. The reaction has to peak that that spot of energy, hit that spot, hit that level of energy before it will go on and make the products. So from there, it's all down. I wanted red. It's all smooth sailing, and eventually you make your products and they have that energy level. Now, reaction diagrams can look all sorts of different ways because not every reaction has products that are more stable. All right, you could draw an entirely different reaction diagram. I'm going to do a different color. Let's say you have reactants that tend to be a little more stable, lower in energy, and then you're going to make some products that are like higher in energy. This is a whole different diagram here. Well, we've got to still have a peak energy level. Let's say it's right there, and then we make our products. You could have a reaction diagram that looks like that. Still, yet again, you can mark off the activation energy as the level from the reactants to this peak up here. So from here all the way to here, look, this one has an entirely different activation energy. Okay, some have really big activation energy, some have lower. So regardless, here's what you see. On a reaction diagram, you got to mark off your reactant, label that, energy level for your products, your activation energy, and then there's one more thing I have not, I just realized I haven't marked off. The difference between reactants and products, the energy level there. So here was our reactant level. Here's our product level for the red line. The difference between these two green lines, that's our change in delta G. Or that's our change in Gibbs free energy. That is our delta G. So if I extended this all the way out here, this right here, this is delta G. I know this graph is looking crazy now, all these different lines, but this is our delta G. This is the difference between the energy of your reactants and your products overall. And then we can also draw one for the blue graph, right? You would mark off the difference between your reactants and your products, that delta G. I feel like our graph looks crazy enough. So if I draw that in, it's going to look a little crazier, but you're going to look at some more examples on the next slide. So you need to be able to label reactants, products, activation energy, and delta G. Those 4 things on a diagram, okay? All right, let's go to the next slide. Everybody good with this? Everybody got it drawn? Okay, here's 3 different graphs with the wildly different looking reaction pathways. We said EACT was the activation energy. So the energy required to begin a reaction, that is the activation energy. And yes, Pernell, determined, there it is, like I said, by efficient collisions. Now you also have to have proper orientation. So efficient collisions is just a big part of hitting that activation energy. But this determines the rate. It determines how fast the reaction goes, whether it's slow or whether it's fast. So if you have a small activation energy, that's going to be a fast reaction because you don't have to have a lot to hit the peak and go forward and make your products. If you have a large activation energy, that's going to be a slow reaction. Now, the last thing I want to make a note, I'm going to put a star by this. I'm going to highlight it. It's a big deal. Activation energy does not affect delta G. It's 2 entirely different things. Okay? Does not affect your delta G. You can change your activation energy all you want. Does not affect the sign of delta G. So look here. I've got A, B, and C. Graphs A, B, and C. You tell me which one is the fastest reaction. A, B, or C? Which one is the fastest?
C.
Person says C. Why do you say that?
It has the smallest EACT activation energy.
Yeah, it does. Look right there. Very little, very small peak. Okay. So that's the fastest. So we could label that. And then on the flip side, which one's the slowest?
B.
Look at the activation energy on B. That thing is huge. Oh, I meant to highlight. Right there. Okay, so this one is the slowest. A is somewhere in the middle, all right? So we started all these reactions at the same time. C would get done first. B would get done last. A would get done somewhere in the middle. And now looking at these, which reaction is favorable? Do we have any reactions that are favorable? Spontaneous. How do we know that? You've got to have a negative delta G. Which one of these graphs has a negative delta G? Molly says A and C. Okay, so here was our delta G. Here's our delta G over here. Here's our delta G on each of these. A and C, as you go from reactants to products, delta G decreases. Okay, products, in other words, are lower than the reactants on the graph. So yeah, these reactions right here, these are favorable, negative delta G, favorable. Negative delta G, favorable. And B is a positive delta G. You see how the products are higher than the reactants on the energy scale? So that's not favorable, non-spontaneous. All right, so I want you to be able to read these graphs and pull some information like this out. Any questions on these? You could draw one if you had to. If I told you to write a reaction pathway for a non-spontaneous reaction, and that's all I said, you could do that. Okay. All right, now if we need a reaction to go faster, how can we make it go faster? There's 3 ways. We can change reaction rates using 3 different properties. Number 1, temperature. Number 2, concentration of reactants. And notice I'm just saying change. I haven't talked about increasing or decreasing. It's different things if we want to increase versus if we want to decrease. We make different adjustments. But I can just manipulate it, change it by changing these things. And then lastly, catalyst. we can add a catalyst. Okay, anybody heard that word before? A catalyst? What is a catalyst?
Doesn't it assist like getting something going?
It helps the reactions go. A biological catalyst, and a fancy word for that is an enzyme. Anybody heard of enzyme? Maybe you take like enzyme supplements, okay, in your diet or whatever. Yeah, those help reactions go faster. All right, so how in the world does temperature change this? Well, if we increase temperature, we can increase the rate. And if we decrease temperature, we can decrease the rate. Okay, in grad school, they had these giant rooms that they would keep like refrigerator temperature. We call them cold rooms. I felt all bad for really bad for grad students who had to go do reactions in cold rooms. You literally had to go stand in this room like all day. So if anybody hates cold weather, they'd have to go do, because they wanted the reaction to go at a slower rate. All right. I never had to do that, thank goodness. Okay, but if you increase the temperature, here's what you do. You're increasing the frequency of collisions between your molecules. Okay, if molecules are moving faster because we've added energy, we've added heat to them, then they're going to collide more often. And the more they collide, the more chances we have at getting the reaction to happen. And we're going to increase the forcefulness of the collisions, increase the frequency and the forcefulness. Okay, if we increase the temperature, we're adding energy and they're moving faster. So when they hit, they're going to hit harder. Okay, it's like hitting two cars hitting at 70 miles per hour versus 20 miles per hour. Okay, which wreck is going to be worse, right? The more hard something hits, the more chance in the world of molecules, the better the chance they have of clearing that activation energy peak and making the reaction happen if they have more energy. Okay, so these things will increase the rate. And then vice versa, if we decrease temperature, we can decrease the rate because we decrease these same two things, frequency and forcefulness. All right, let's talk about concentration. First of all, what does the word concentration mean? We haven't even defined that. I like to think about it like this. Anybody had lemonade before? Anybody had really bad lemonade? Bad lemonade is bad lemonade because why? Tastes like really watery, right? It's just not enough. There's not enough of your actual, country time powder in it, okay, or whatever. But bad lemonade, it's too diluted. It's not concentrated enough, okay? So concentration is a measure of how much stuff is dissolved in your liquid. And molecules are things we dissolve in solutions. Okay, so we can discuss the concentration of these things. So if we increase the number of molecules in a given solution or in a given space, we're increasing the concentration. So if we increase the concentration, we increase the frequency of collisions. Okay. It's like 2 people on an elevator or 20 people on an elevator, okay? Obviously, people are going to bump into each other more the more people there are. Okay. Now we're not increasing the forcefulness here because we're not making those molecules move with any more speed or any more energy. But they're going to bump into each other more often, and the chances of our reaction to happen increase because of that. If you want to decrease the rate, then you can decrease concentration, right? Okay, lastly, a catalyst. So we defined this earlier. Somebody, I think Blake said it was a substance that helps it go faster, but yes, it's a substance that increases the rate of a reaction, but is not used or altered in the reaction itself. It's not used. It's a totally separate thing from the reaction. It's just there to help make the reaction go. So how does it do that? Well, a catalyst lowers the activation energy. That's how it makes the reaction go faster. It minimizes the peak energy that our molecules have to hit for the reaction to go. It does this a couple different ways. It can create an entirely different reaction pathway. It can help hold our molecules in just the right angle and right orientation. Or it can just help bring the molecules closer together and give them a better chance of colliding in the right way. So this is the way we'll look. If we have some reaction pathway that looks like this, reactants, products, and then here's our EACT, right? I'm going to draw another reaction in blue. Let's say we have the same reactants and then we add a catalyst, and it's just going to lower that activation energy. It'll still give us the same products. So this blue one is with a catalyst, and this red one is no catalyst. So it just lowered the activation energy. That's all it did. Whoops, I better write that in blue. Okay, questions on this? Are we moving too fast? It's 9:11, so we're almost done. Would you mind going back up to the concentration slide? Yes, Whitney. There we go. Okay, I think, Whitney, are you good? Okay, I think that's it for reaction rate. So I got one poll question to kind of end this thing here. I want to review Gibbs free energy. So fill in the blanks for me right here. It says a reaction with a positive delta G is known as a what kind of reaction? Exergonic or endergonic? And does that mean it's favorable or unfavorable? A reaction with a positive delta G, known as exergonic or endergonic, and does that mean it's favorable or unfavorable? So based on what we talked about with sign of delta G, if it's a positive delta G, do we say that's exergonic or endergonic? And does that mean it's favorable or unfavorable? So give you about 10 more seconds. I don't see the numbers going up anymore. Okay, barely. So get your guess in. All right, I'm going to call the poll. So most people said endergonic and unfavorable. And if you said that, you are correct, okay? Positive delta G, that's an endergonic reaction. And that means it's not favorable, not spontaneous. Okay, so today we finished up entropy. We talked about Gibbs free energy and how all the pieces, the delta H and the delta S, come together to give you the delta G. And then we talked about rates, how you can change reaction rates. We drew energy diagrams. Those are the big things from today. I'm going to stop sharing my screen. Remember that you have a quiz today, okay? Quiz 7.